All right, resonance structures. There are two instances when resonance structures are possibilities. The first instance corresponds to a case where you have multiple bonds present in your Lewis structure, and you have a fulfilled octet for all of the elements. In particular, the central element has its octet fulfilled, but the other thing to notice is that the bond that has the multiple bond has an atom next door, atom X, that has lone pairs. And whenever you have a group that has lone pairs next to a multiple bond, whether it is a double bond or triple bond, you can undergo resonance. In particular, the electrons from the neighboring atom can be donated to the central element. And since the central element has a complete octet, you have to remove a pair of electrons from the multiple bond. And what ends up happening is that you end up creating a new multiple bond between the central element and the neighboring element. And where you used to have a multiple bond, now you only have a bond that has one less multiplicity than it used to have. So it used to be a double bond, now it's a single bond. Also, I would like you to notice that the charges do change. And ideally, the way this goes is that for the element that is donating electrons, you increase the charge by 1 for every lone pair that you donate. And for the element that is receiving electrons, you decrease the charge for every lone pair that you accept. And notice that the central element didn't change charge because it did accept a lone pair of electrons. That should decrease its charge, but at the same time it is giving away a different lone pair of electrons or a different set of electrons. That's increasing its charge. So that -1 and +1 basically cancel each other out, giving you a neutral central atom. Alright, the other instance where you may see resonance structures is when you have um, a central element that is not yet fulfilling the octet rule. It has less than 8 electrons. This is an electron deficient center. But the elements next door do have lone pairs. And so those elements next door can actually donate the lone pairs and complete the octet for the central element. At the same time, you're going to develop charges. And although the initial structure doesn't have charges, it's better to go with the one structure that does have charges because it's fulfilling the octet. A typical example is sulfate. Sulfate is written as a tetrahedral molecule where the sulfur bears the central element or the central space, and the oxygens are simply placed around it. Now, when you consider the total valence electrons of SO4 2-, what ends up happening is that you end up coming with a structure that has 2 double bonds between sulfur and oxygen and 2 single bonds between sulfur and oxygen. So what ends up happening is that you can alternate where the double bonds and single bonds are present in the molecule, and each one of these structures right here represents a different resonance structure of the sulfate anion. To show you step by step how this goes, you could start with the molecule here on the upper left corner, and to go from this structure to the next, we have to bring electrons from the left oxygen to the middle element, the sulfur, and we have to kick out one of the lines of the double bond from the upper oxygen towards the oxygen itself, and so we end up with this structure here. As I explained before, the atom that gives the electrons away, which was the oxygen here, is going to increase its charge. It was -1 to begin with. Increasing its charge will make it neutral. The oxygen that is receiving electrons is going to have its charge go down. It's neutral to begin with, now it will be -1. And same idea right here. To get the structure that we have here on the right side, we have to bring electrons from the oxygen on the right side, and we have to remove electrons from the oxygen on the left side. So oxygen on the right side increases its charge as it's giving away electrons from -1 to 0, and the oxygen on the left side decreases its charge from 0 to -1, as it can be seen here. The same procedure can be applied every step of the way until basically you go through each possibility of rotating the double bonds from one direction to another. All taken together, what we're really seeing is a picture of average double bonds and single bonds, because at any given time, two of the oxygen sulfur bonds are double bonds, while the rest of the sulfur oxygen bonds are double bonds. But you could have them located on any which one of these oxygens. It doesn't really matter if they're opposite of each other or right next to each other. As long as two of them are double bonds and two of them are single bonds, you have the correct Lewis structure, or at least one correct resonance structure of the Lewis structure. So on average, what you're seeing is that you will always have a sulfur oxygen single bond. That's never going to change. But for some of the time, half the time, you're going to have a double bond between the sulfur and the oxygen. And then that double bond character kind of rotates throughout all four of the oxygens. So in reality, the bonds are not exactly single or double, but they're rather 1.5 bonds. And more importantly, the charge. The charge of that sulfate, half of the time it's -1 on the oxygen, half of the time is neutral. So that basically tells us that the average charge on each one of the oxygens is -0.5, and if you add them up together, that gives you -2 charge of sulfate. But the idea is that now you're spreading out that negative charge, and in doing so, you're basically diluting the charge. And decreasing charges, generally speaking, stabilizes the structure. So this is the power, one of the powers of resonance structures that we can utilize. And this is why they happen. You're trying to stabilize the molecule as much as possible. Another thing that resonance structures can do for us is explain, or at least give us a means of explaining why the reactivity of molecules takes place the way it does. So to give you an example, we could have this molecule over here known as aniline, which contains this aromatic six-member ring bound to an NH2 fragment. And we could have the same molecule down here, but in addition to all of the aforementioned, we also have an NO2 fragment, completely opposite to the NH2 fragment. And what we find out experimentally is that this particular equilibrium of giving away the H+, in other words, the equilibrium of the molecule, the organic molecule behaving as an acid, favors the molecule down here that contains the NO2 fragment. In other words, the molecule here on the bottom fragment is more acidic. And we can explain that with resonance structures, because we can look at the NH2 fragment that has a lone pair, and we see that next door we have an atom that bears a multiple bond. So this is spelling out resonance structure. And also, another thing I'm going to tell you right now, which this is going to kind of help us get all of them at once. In this type of aromatic ring, the six-member ring with the three double bonds, you could actually rotate all three of them at the same time and generate an equivalent structure, shown right here, where the double bonds are now alternating. They are in the three different positions. So we alternated the double and single bond characters in the molecule. But now, as I was saying, the lone pair of the nitrogen, which is next to a carbon that has a multiple bond, spells out resonance. So we're going to bring those lone pairs onto the central carbon. And since that carbon has a fulfilled octet as is, we need to kick away one set of electrons from the multiple bond onto the next atom. So there's always going to be this triad of atoms where this happens. And notice here on the bottom portion, we're still doing the same thing, but because the multiple bond is now on the left side, we kick out the electrons towards the left side. Alright, so what ends up happening is the following. We have now creating a double bond between the nitrogen and the carbon directly connected to it in both of the structures. And now we have also generated a carbon that has a lone pair associated with it, either on the right bottom carbon, or left bottom carbon, right? You could also determine this negative charge by using the charge formula. Each one of the hydrogens is assumed to have a single bond connected to the individual carbon. So this carbon has 3 bonds and 1 lone pair. So you'll find out via the formal charge formula that this carbon ought to have a -1 charge. All right, now the new lone pair that we generated is next to another carbon that also has a multiple bond. So guess what? We have another resonance structure that we can utilize here. So let's do that. We can move that lone pair onto the next carbon, and then we need to kick away a set of electrons from that carbon since it already has a fulfilled octet. And this generates the following structure. Now, whether you start from the top or the bottom segment, you end up at the same value right here, the same overall structure. One where you have now a carbon with a lone pair opposite to that carbon that bears the nitrogen carbon double bond. And the carbon right here is next to a nitrogen that has a multiple bond next to it. So guess what? You can actually draw a resonance structure for that particular fragment up here. And in doing so, you will create this new carbon-nitrogen double bond and your nitrogen-oxygen single bonds. And notice the charges. The nitrogen has a plus charge to begin with. You bring in electrons, so its charge should decrease. But at the same time, you're kicking away electrons from the nitrogen-oxygen bond away from the nitrogen. So the charge increases once again. So you end up not changing the charge of the central element. The only charges that really change are the external ones of element 1 and element 3 in the triad. Alright, so here's the deal. Up until this resonance structure, if you do the same thing with aniline, the one that does not contain the NO2 fragment, all these resonance structures are present in aniline itself. However, the last resonance structure is not. This is unique to the nitro derivative. And so it is this resonance structure that is responsible for the higher acidity of the molecule. And the reason why is because you have one more alternate way of forcing the nitrogen down here to have a positive charge. Notice that in the second set, the third set, and the fourth set, the nitrogen has that positive charge, making the hydrogens more electron deficient and more susceptible to deprotonation. So anytime that you can extend the amount of times that that atom bears a positive charge, you make it much more likely for it to be acidic. So as you can see, resonance structures have a strong power of predicting whether or not certain reactivity traits of molecules can be rationalized or not. Okay, so that's it for this video. I'll see you in the next one.